talk about the geometric learning, and the main problematic that you will try to give an answer for is the following one. What about the challenges related to learning from non-Euclidean domains via the presentation of basic architectural solution for graphs, point clouds, and meshes, and it will give us some example related to relief pattern on 3D mesh surfaces, another example on the generation of 4D emotional faces, and also another one about the talking heads. And then, after the question-answer session, we're going to get a coffee break. And at the end of the coffee break, I'd like you all to be present outside to make a big and outstanding photo in terms of souvenir, okay? And then we're going to begin the conclusion of these 2 days, that is to say, a Moroccan applied use cases, and then the panel. And the objective of the panel will be to make a kind of summary done by each of the experts present with us today, and to discuss about it, and to fix the major issues, or we're going to say the most important trends that should be addressed for the next year in the field of multimodal AI and computer vision. At the end of the panel, we will all be able to announce what should be the content of the next AI Spring School. Mr. Stefano Berretti, thank you for your presence. Show must go on.
Okay.
Thank you.
Thank you very much again. I suppose that most of you did not study this subject in your regular courses, and then at the end I will present some scientific results, some research results. So let me first of all introduce the idea of geometric learning. In the talk that we had yesterday, for example, we have seen many results using images and videos. And we know that the characteristic of images and videos is the fact that we have a uniform grid of pixels. And so we have a number associated to each pixel or a color vector. But things can be different if we move from the flat domain, the Euclidean domain, to a geometry domain. That means that it is something that is non-Euclidean, basically is a manifold, is a curved surface in this specific case. And so in this case, we say that this is a non-Euclidean domain. So it is not flat, but is a curved domain. So more in general, geometric learning, and so the non-Euclidean domain is something that is related to point clouds, graphs, but also splines, tetrahedral meshes, and other different domains.
Professor, please, can you speak in front of the mic?
Okay, yes.
Thank you. Yeah. If it's possible, if needed, you can give...
Yes. No, I can maybe use it this way. Okay. So, first, maybe the easier way to start is saying something about shape, because it is something that we know in the real world. So, as I took this sentence from one of the first researcher that worked for shapes. So, shapes is something that exists in the natural sciences, and in our world, as a mathematical object, basically a shape is something that is that allow us to pass from a continuous domain, as in the left you see a sphere, but then we can make it locally represented in a discrete way. So we can pass from the continuous to the discrete world with a local parameterization of the surface. The two domains, the shapes and images, are very different. So you see on the left the Euclidean flat domain, and on the right the non-Euclidean curved domain. And so we can have for this non-Euclidean domain, we can have several different representations, differently from the array of pixels that you can see for an image. So we can have splines, we can have a graph, we can have point clouds, we can have triangle meshes. And so we have also different parameterization, because for images we have a global parameterization, which is given by basically the axis of the image. But in the case of shapes, in most of the cases, the parameterization is just local, so not a global one. And we have also different transformations, because for images we have, for example, a perspective transformation, affine transformation, but for shape in general, the transformations are non-rigid transformations. So they are much more general than single categories. Additionally, also for images is quite simple to make computations, because, for example, we can, in the upper part of this slide, you can compose two images in a very simple way, because you can add together these two images. But it is more difficult to define this concept for example, a 3D shape like in the lower part of this figure. So what does it mean to compose together, to add together these two shapes? As I said, shape can have very different representations. So we can have point clouds, triangle meshes, implicit surfaces are probably the most common, but other exist. So we can have polygonal meshes or parametric surface, or even volumetric representations that are more close to the Euclidean domain, because you can think to add basically a third dimension to the representation. Here you can see some examples of these different representations. So with a mesh, with volumetric, with different type of meshes. And so to start and to conclude this very simple introduction, I want just to point out the fact that this geometric learning terms was probably first introduced in this paper by Bronstein and LeCun as probably the most known authors. And so the geometric deep learning at the beginning was mostly referred to graphs, but now we will see that geometric deep learning can be, as I said, applied to several different representations. So the idea is that I want to give you some introduction for different domains, so point cloud, graphs, and meshes. So let me start with the point set. So the idea of point set basically is that we have a set of points that are located in the three-dimensional space. So for each point you have three coordinates, the x, y, and z. And this type of data can be acquired, for example, by sensors like a LiDAR. So can be something that can be very useful in a common world application. So here you can see that we can, for example, imagine to obtain this point cloud in different ways. As I said, on the right you can see a KeyNet scan of a real-world object, a person. And on the left you can see that we can imagine also to model, for example, a 3D shape, and then just take the points of this modeling as the set of points. So let me give you an overview of the way we can try to manage this set of points, and the way we can try to learn something from this set of points. So first of all, we can start from a set of nodes, the set V, and for this set we have a number of these points, and we can have a feature for each of these points. So at the end we can construct this vector x, which is basically obtained by considering all the points in the set. And as you can see, these points actually have an ordering. But actually, we would like that the network that tries to learn something from this point should be able to learn something not depending from the ordering of the points. So the idea is this one, you have this set of points, and we want to learn a function from this set of points. And the idea is that this function should produce the same result even if we change the order of the point. So this is one of the first something that we need from this representation. And so here you can see the idea is that we can model this change in the order by considering an operator which is a permutation. So we can think a permutation that makes the initial set to a different order. So you can see, for example, in this example here, that A is then mapped to position 3. So the first point is mapped to position 3, and the second point keeps its position, and the third point is moved to the fourth position, and so on. So permutation can be modeled by a matrix which has the same dimension of the set. And so you see here that basically this operation can be modeled by applying this permutation matrix to the set of points, which is the input. So this matrix here has 1 for each row and each column. And so you can apply the matrix and pass from the original set to the permuted one. And so to obtain permutation invariance, basically we would like that this function f does not depend on the order of the points. So said in a different way, we would like that if we apply the function f to the input set x, and we apply this permutation to the input set, basically the result is the same. Professor Mubarak yesterday introduced something similar applied to images, and here the concept is more or less the same. This is the case of invariance to permutation. So deep sets is one of the first work that tried to model this using a neural network. So the idea here is that the two functions, psi and phi, are some learnable functions. So basically they could be some multi-layer perceptron, and an operator that can be used to aggregate the function applied to individual points is something that should be invariant to the order. So for example, a sum or a maximum or an averaging operator. So all these operators are invariant to the permutation of the elements of the set. So more in general, so we can substitute the sum here with this permutation invariant operator. So this is the general representation that we can have for a network that learns from a set of points. Another important concept that, again, Professor Shah introduced yesterday is that of permutation equivariance. So in this case, the question is that one: what if we would like answers at the node, so at the point level? So in that case, we want to still be able to identify the outputs of the nodes, but if we use simply a permutation invariant aggregator, that aggregator would destroy the output. So in this case, we seek for a function that doesn't change the node order. So the idea is that if we permute nodes it doesn't matter basically if we do it before or after. So mathematically, this can be expressed in this way. So we are seeking for a function big F that applied to a permuted set Px is the same as we applied the permutation to the function applied to the initial set. So this is the concept of permutation equivariance. Another important thing that we would like to have from this network that learns from a set of points is the fact that we would like to have some locality. It is a concept similar to the convolutional neural network where we apply the kernels which are local, but then the network is very deep. So here we would like to obtain something similar for a set of points. And so in this domain, basically, we can enforce locality through a shared function, C, which is applied to every node in isolation. So the idea is that if this function is applied, which again can be a part of the network, can be applied to the nodes independently, then we can stacking the output into a matrix, and so this matrix basically inherits this property of being equivariant to permutation. So the idea, of course, that if we can apply separately, at the end we can permute. And so this is more or less the conclusion that we obtain for point set. The idea is that we should have a function that is applied individually on points, so we can share this function between points, and then we can compose stacking this equivariant function in using an operator which is invariant to permutation. So again, a sum, an average, or maybe a maximum operator. This is one of the basic results, and can be also shown that more or less, if we want to obtain these two properties, more or less we have something that can be modeled in this way, so through this deep. And so now I want just to show you a very well-known model, but probably most of you have not studied this one. So let me go through some details about the point net architecture that was one of the first architecture proposed for the point set domain. And the proposal was for learning from point set so as to be capable to retrieve and so classify similar objects. And on the left, you can see that this network can be also applied for segmenting 3D point clouds. So in the example, you can see either models that have been obtained using CAD software or something that simulates Kinect scans. So the point net architecture, basically, we can see that has some concepts that are very similar to the deep set. And so it can work on points that are so not ordered. So the main properties are that this network is capable to work with permutation of points. So the network is independent from the order that we use for the points. And it is also invariant to some geometric transformation, because in the 3D domain, of course, we have a set of points that can be rotated, translated. So we expect that the representation that we learn is in some way invariant to this geometric transformation. And then for the segmentation part, this network tries also to capture information about the proximity of points in 3D in order to segment, because of course segmentation is something which is based on local properties, while classification is more related to global features of the point clouds. And so here you can see the overall architecture of this network. So I will go into some details for the different blocks. So you can see here that the input is given by a set of points. So we have n points by each one with the 3 coordinates, the x, y, and z. And I will say something about the transformation later, but now let us focus on the embeddings. So the idea is that we apply this multi-layer perceptron, as you can see, to each point independently, but this multi-layer perceptron is shared by all the points. So it's exactly the idea that I presented before for the deep sets. So here, this multi-layer perceptron as the first one has the objective of increasing the dimensionality of the space, and then an additional one again improves or better increases the dimensionality of the space. So we have two global, local actually, and a more global embedding for the points. And then we have the last two layers are used for basically with max pooling is the operator, as we have seen before, for the deep set that allow us to be invariant to the permutation, because of course it is an operator which is invariant to permutation. And then after that, of course, we can have a classification, standard classification layer that uses 3 layers for classifying the input shape. So this is more or less the pipeline for classification. And for the segmentation network, instead, the idea is that, as I said before, the segmentation depends from local properties. And so in this case, the local embedding is concatenated with the global feature. So we have a feature vector that both combines local and global features. And after this, we can apply again a multi-layer perceptron to reduce the dimensionality. At the end, the result is basically a matrix that has the dimension of the points multiplied by the number of possible segmentation classes. So at the end, we have the probability that each point belongs to an individual class. Then just a comment here on the 2 blocks for the transformation, the geometric transformation that allow the network to be invariant to translation and rotation. So we have these 2 input transform and feature transform blocks that are inspired by this spatial transformer network, which is actually not a transformer, but is a network that works in that way. The idea is that this spatial transformer is capable to orient, more or less rearrange the position of, in this case, these digits, and so that the subsequent steps are more easy to perform. Similar idea is applied here, and so this input transform actually works, the first one in the domain, the geometric domain of the input feature. So basically, a 3x3 rotation matrix is learned, and this metric is applied to the point in order to have a normalization of the position. And the second spatial transformation network is actually applied in the feature domain. So in that case are the features that are aligned in order to make them in some way invariant to rotation and translation. So this is the idea of the point net. Then another well-known work in this domain is the point net plus plus that tries to extend, improve the way the point net classify and segment objects. And just a slide here to show the very basic idea, which is that of having some subsequent abstraction of the original points. So basically we are sampling and grouping together the initial points, and then the point net is applied repeatedly on this sampled and grouped set. So doing this at different level, we have a representation that has a different level of granularity, more or less. And then the subsequent steps follow more or less what we have seen for the point net. So we have a pipeline for the classification and the other one for the segmentation. So this more or less, the idea here is to provide you an idea of what is the objective and the main functionalities that we can try to apply to learn from point sets. The subsequent step is that of trying to extend the point set with some links, so passing from points that are separated each other to graphs. So the concept of graph is more or less well known, because we have a graph in several different domains. Here you can see some of these domains. And graph neural networks are more or less applied in very different domains. So these are just some abstracts that I catch here and there. Graph is also a concept that is very important in the normal life, because probably also the way we model the world is based on some concepts and relationship between these concepts. And so it is also something that is expected to be very important in order to have some general artificial intelligence. So having an idea of how to learn from this non-Euclidean domain is something which is really important. So in this case, the difference is that different from what we have seen before for point clouds. In this case, we have also a set of edges. So a graph is a set of nodes and a set of edges. And the idea is that the relationship between points can be modeled by an adjacency matrix, where the elements of this matrix are given by 1 and 0. So we have a 1 if there is a connection, and 0, of course, if there is no connection. And so also in this case, I try to keep this formulation where our desiderata is that of having a representation which is permutation, invariant, and equivariant. And so let me try to show quite briefly how this concept of invariance and equivariance changed in the case of graphs. So this is what we have seen for points. And for graph, we have more or less something similar. So the idea is that we would like to have the same output, even if we keep the same connection between the nodes, but we, as you see on the right, we move these nodes, but connection are still the same. So we would like to learn the same representation. So the difficulty here is that now permutations can be applied also to edges, not just to points. And so in this case, we can permute both rows and columns of the adjacency matrix. So this can be mathematically formulated by this permutation matrix that can be applied to both the set of points and the adjacency matrix. So again, we have the invariance, that can be modeled as you see there, and the equivariance that again means that this big F function should be the same if it is learned from the initial set permuted, or if we permute the results provided by the function when applied to the original data. So another difference that we have with respect to the point set is that in this case, while for the point set each node is elaborated, is transformed in isolation, here each node has some neighborhood. So we have to take into account this neighborhood. And so the one definition is that of one-hop neighborhood, which is represented by the nodes that are connected to a given one. So given the node I, Ni is the set of nodes that are connected to that one. And so we can define these neighborhood features, which are the features of the nodes that are connected to the node I. And so we can also define a local function phi that is that operates on the central points and its neighborhood, or better, on the features of the nodes and of its neighborhood. And so, in order to have a permutation equivariant function, in a similar way to what I presented before for the point set, we have to apply a local function phi over all the neighborhoods. So in a similar way that we use for point set, where the function was applied independently for the points. And so in order to have this equivariance, it is sufficient that the function phi does not depend on the order of the nodes in the neighborhood. So if this operator phi is permutation invariant. And so this is basically the idea of what we would like to do. So we have these nodes with its neighborhood, and we want to learn this function phi that maps the node to this learned representation, take into account the neighborhood of the node. And so, with this idea in mind, we can have some example of what we can learn on graph. So you see that we have an input, which is given by the set of points and the related features and the adjacency matrix. And the graph neural network is something that learns this latence, so this space H, with the adjacency matrix. And so we can imagine to perform different operations. We can learn different things. So, for example, we can classify nodes, as in the first example, or maybe we can classify graphs. So in that case, you see that we have some operator that should be invariant to the order of the nodes, which is learned from this latent representation. And finally, you can also try, for example, to predict some link in the graph. So in that case, the function is something that is learned from the latent representation of two nodes that are connected together by one edge. So this is actually an area of intense research, because of course we can have different way we can define this function phi. So the function phi can have also different names. It can be referred to as diffusion, propagation, or message passing. And the big F instead is the graph neural network layer. So the interesting thing is that at the end we can more or less all these different ways we can try to learn from this data can be classified into three main flavors. So I can try to show you these three different ways. Normally we can classify the way we work on, we learn from a graph. So on the left we have the convolutional the attentional and the message passing solution. So let me just give you some more details for each one, but very briefly. So in the first case, the idea of a convolutional graph neural network is that of having something that is learned in that way. So the C, I, J are basically the constant fixed weights. So in that case, we have a fixed weights between two nodes, for example, as you can see in the figure. So this is the simplest way to learn something from a graph. And this is a convolutional graph neural network. The other case is that of attentional graph neural network. In this case, instead, we have some attention weights that are modeled by that alpha weights. So these weights are actually something that can be modeled as something that takes into account the relationship between the two nodes and the features that are attached to each node. The limitation of this model is represented by the fact that these alpha weights are some scalar. So the most general representation that we can have for a graph is represented by the message passing graph neural network. In this case, actually, we can compute arbitrary vectors, which are indicated in the language of graph neural network as messages. And so these messages basically are computed by C, which is more or less a layer of the network. So this represents the most general representation that we can have in this domain. So this is more or less a very short overview of what we can learn from graphs. So you have you can have in this way a very basic idea of which are the basic operations that we can apply to graph. And so moving ahead, we have another. I would like to introduce you also in this case with an example of a basic architecture, the case where we generalize the convolution on meshes. So meshes is a very specific domain because in this case we have a collection of points that are connected together by a sort of graph, but in most of the cases this graph is very particular because you see that we can have some relation which is given by, for example, having triangles that model the surface. So it is similar to a graph, but here we have a more specific domain, and so we can try to exploit the specificity of this domain in order to have solutions that are more tailored to this case. So also let me just introduce you some very basic concept about a triangular mesh. Triangulation is normally used because it is needed in most of the cases for rendering, for example, a 3D shape, but also because the triangle, of course, is the most simple way we can connect together a set of points. So in what we normally, when we apply a learning method to this domain, with the hypothesis that we have a mesh which is oriented, so normally we have a counterclockwise ordering between the vertices, the nodes of this mesh, and we have, of course, a normal which is obtained by cross product between the side of the triangle. And in addition, normally we consider manifold meshes. Manifold means that more or less the surface is something that has, like in that case, faces that go outside the surface. So in that case, for example, for one edge, we have 3 triangles. So this is something that is not admitted in this domain. And the other 2 figures represent a closed fan and an open fan. So a connection, a valid connection between a set of vertices. And here you can see again some cases that are not considered when we learn from meshes. So we do not want, of course, some triangles which is positioned in a very bad way, so that makes the mesh not manifold. And of course, we have the normal, which is something that we can obtain with these rules of the right hand. And so here, as an example of how to learn from this domain, I want just to show you again a basic architecture, which is quite old, but can give you an idea of how we can tailor some architecture on this specific domain. So the idea here is that of more or less redefine, replicate what we defined for a convolutional neural network in an image domain. And so the basic idea here is that of define a local patch where we can redefine a convolution. Because if we want to learn using the idea of convolutional neural network, what is missing in this domain is an ordering between the vertices. And so in order to have this ordering, the idea is to have this local parameterization that in this specific case is obtained by considering some level sets. These level sets are obtained by considering different radius, so different distances from a central point. And we have also some angular coordinates which are obtained by having a geodesic path from the central point along some angular direction. And this, of course, this radial direction intersect in a perpendicular way the level set which are concentric to the central point. And so we can obtain something as represented there on the right, a local parameterization of the shape. And then with this local parameterization, then the idea is that of having like a patch operator. A patch operator is something that basically interpolates a function defined on the mesh. So normally this function can be defined on the vertices, and this patch operator is the value for this local parameterization. Once we have defined this parameterization and we have an operator that can sample the function, at the end we can redefine convolution having a local filter with some particular weights. So in that case, that A is the filter that can be applied to the patch. You can note here that in any case we have some ambiguity for what concerns the rotation of the filter. So in that case, in this case, it is required that we apply the filter for different angles. So we have this more complicated way to apply this filter. Here you can see, you can have an idea of the way this patch operator can be defined. More or less, it is a Gaussian that weights the function in this local patch. So you can see on the right the weights that are assigned to radially and according to the angular direction. So basically, as I said, the idea is that of sampling this function f in the different part of this local operator. So with this local parameterization, we can more or less replicate the structure, the architecture of a convolutional neural network. So at the beginning, there is in this specific architecture a linear layer, which is applied to adjust more or less the input and output dimension by means of a linear combination. And then, for example, we can have a standard rectified linear unit. And after that, we can apply this geodesic convolution. So this is an example of how we can redefine convolution in this carved domain. Having these patches and having these patches, we can redefine convolution in this way. As I said again, the complication in this case is that we have to replicate this filtering for several different angles. And so due to this, after that, we need also to have an angular max pooling, which is a max pooling applied to the bank of filters for different directions. So you see that filters provide some output that then is collected by this max pooling operator. And then at the end, we have some standard layer for performing, for example, classification, as in this case. And going to the conclusion also for this part about convolution on the mesh, let me spend some words about the spiral convolution, which is a quite important operator that revealed to be quite successful in several different applications. So in the example that I presented, basically the idea is that of aggregating the neighborhoods of a node by learning some weights. The idea of a spiral convolution instead is different because the node features and are encoded under an explicitly defined spiral sequence. So the idea is that giving a point, we can predefine which is the sequence of neighboring points. So of course, this has some limitations because in order to apply this operator, we need that meshes are all in the same, all share the same parameterization. So all have the same number of points, and these points are ordered in the same way. If this is true, we can define some, we can define these spiral sequences, and we can also have some matrices that are used to subsample the input mesh. And so the idea actually is quite simple of the spiral convolution, because you see we have a central point, and then deciding one specific direction, we can go in a spiral way, and so we can have the set of points that are the neighborhood of the central one. So the idea is that of following a counterclockwise or clockwise direction for collecting these neighborhood points. And so, as I said, these spirals can be pre-computed only once. And here you can see also that it is also possible to increase the receptive field by, for example, using a different sampling that allows to keep the same length for the spiral, but enlarge the support of this spiral convolution operator. Okay, so this is a quite very basic introduction to this domain, but I think that probably can be useful if you have never seen this specific kind of data in your previous study. And so now, to conclude my presentation, I want to show you some applications that are more in the domain of generative AI, which is one of the topics of this school. And so the applications are for 3D dynamic face and also for body. So the first application that I want to show you is for 4D facial expression generation. So actually there are very few works on this topic. The idea is that of starting from a neutral 3D face model as represented on the top of the slide. And what we would like to obtain is an animated face, but just giving as an additional input the label of the expression. So for example, you can see there some examples animation where we have different labels, so mouth up, mouth side, and so on. And so starting from this neutral face, we can keep the identity and animate the face. Of course, this can have several different applications going from, for example, designing games or maybe also interaction. And so we can, this can have several different interesting applications. So let me show you some previous works in this domain. Actually, as I said, there are just a few works, at least when we presented this work 2 years ago, but also recently there are not much on this topic. And actually, the previous works mainly focused on the use of morphable model. You know, morphable model is a model of the face that can be deformed on a target image. And so in most of these cases, the model was deformed on individual frame of a sequence in order to animate. So the control in most of the cases was given by frame. In our case, instead, we have just one label as an input, and we are able to generate different emotion given a label and the noise as an input. So here you can see an overview of our solution. So we start, as I said, from a label, an expression label, and the noise. So N is the input noise. So we are able from this noise to generate some difference between generated sequences. And the idea is that we have two parts in this architecture. We have the motion 3D gun, which is used to actually generate the animation, and the second part, which is used instead for passing from landmarks that are generated in the animation to a dense mesh. So let me go in some details into the different blocks of this architecture. So the first important thing is about the way we model the motion. The idea is that the face is modeled by a set of landmarks, as you can see on the left. In this case, if I remember well, we used the 68 landmarks, which are positioned in some relevant points of the face and can be, for example, or detected or maybe manually annotated. And so here you see that our idea is that we want to animate these landmarks that are given in the static input phase. So we want to animate these landmarks. And here we use the special representation, which is represented by this square root velocity function. This function is capable to capture, you see, something related to the first order derivative of the input, so it's something related to the velocity of those landmarks. And so basically that alpha, the input, is like a point in a space that has a dimension 3 multiplied by m, where m is the number of landmarks. And so these points, it can be proved that that representation maps this input vector to a sphere. So the qt is something that lies on a sphere in a high-dimensional space. So this sphere has a radius equal to 1, actually. And it is also possible to show that if we have the initial condition, we can pass back from this sphere to the space of landmark. So we use this special representation, and we use this representation to design a GAN network. So the GAN network actually learns on the sphere. So in the next slide, I will provide you more detail. This is basically the big picture, the overview of the overall process. So let me go into some detail about the generative adversarial network, which is presented here. So the architecture is that of generative adversarial vector. So network. So we have a generator in the lower part. You see that the generator takes as input the class label, which is represented as a one-hot encoder. So we have one for the label, which is activated in a certain as an input. And then we have also noise. And the idea is that the generator it generates on the tangent space of this sphere. So we locally linearize the sphere, and the generation is on this tangent space. And then we can use this operator, the exponential and the logarithm operator, to go forth and back to the sphere. So with the exponential, we can pass from the tangent space to the sphere, and with the logarithm operator, we can do the opposite, so going from the sphere to the tangent plane. And so, as in a, let me say, normal GAN, we have this a loss which is composed by a reconstruction loss. So we compare the on the tangent space the generated and the true input, and we have also the adversarial loss. So it is something which is related to the discriminator. So in that case, of course, we play this in the way that the generator tried to generate samples that are indistinguishable from the real one. And so the adversarial loss is a Wasserstein adversarial loss, and so it is something known in the literature, and the formulation is that represented here, where we have the normal, the terms that account for the generated and the real distribution, and the one term that accounts for generating a smooth output. And so at the end, with this representation, we are able to generate one sequence as a result of a generator on the sphere. And this sequence actually is represented by a set of landmarks, a set of points. Actually, we worked with the displacement. So what we generate is actually the displacement between the neutral input phase and the generated one. Once we have these landmarks, we can apply spiral convolution. So exactly the operator that I presented a few slides ago. And so this spiral convolution is applied to more or less densify the set of landmarks. So we want to pass from landmarks to a mesh. And so we can do this with this spiral convolution. And also in this case, we have some special loss. We have a reconstruction loss on the displacement. So this is quite standard. But we have also a loss that accounts for the distance between points and the landmarks of the phase. And so since we are working with the landmarks, at the end we have also to sum up the neutral mesh in order to have the final sequence. So in this case, this network here works frame by frame on the generated sequence. Okay, so here we have some results. Okay, so this show that compared to the literature, our work is capable on 2 different datasets to drastically reduce the error, both if we consider unseen expressions, so we train on some individuals with some expressions, and we test on unseen expressions, and also if we test our model on unseen identities. This means that we, during the training, the network see all the expressions, but then is capable to generate new, to reconstruct also new identities. And in addition to this, we also try to train a classifier that use these generated sequences as input, and also in this case we can demonstrate with these results that the generated sequences are quite similar to the ground truth, so to sequences that are real one. So this is a very simple classifier based on an LSTM. And here you can see some generated sequences. So you can see that actually the movement is quite smooth in most of the case, even if these expressions are quite asymmetric, and in some cases they are also exaggerated. But our network is quite robust to these difficult meshes. We also tried some other different applications. So here you can see that we are able to interpolate between different expressions. So we have eye smile, and we can interpolate to mouth side in a quite good way, and the same in the lower part of the slide. And here you can see that we can also animate a talking face, also, even if in this case actually the generation is not controlled by the speech, but we just take the landmark from a talking head and then apply this landmark to animate, so to reconstruct the face. Okay, maybe because the time probably is running, maybe I can skip, because this is an extension of this work where we show that we can also generate sequences with several expressions. So we are able to generate sequences that have a longer duration, and we can translate from, we can pass from one expression to a different one. So you can see that the error in this case increases, but for many frames it does not divert. So we can pass from one expression to another. But I prefer to probably show you something different, which is this work that we presented last year in September on 3D talking heads. In this case, the idea is that we start from a speech, so from an audio signal, and we want to animate a 3D face. So again, the input of the system is given by a 3D model, which is static, and represent a subject with a given identity, and then we use the speech to animate the lips movement. So this is quite, of course, a difficult task, and I will show you that we can obtain some interesting result. So here you can see the general architecture. So as an input, we have the speech. Then we again pass from, in this case, from the speech to the landmark. So the idea is that the generation is again in the landmark domain, because this, in our case, proved to have some advantages, because we have to control a limited number of points, and we can then, from these points, using the same decoder as I presented in the other work, we can then reconstruct, densify the mesh, and so pass from the landmarks to the 3D mesh. So in terms of the architecture, we use this WAV2VEC encoder to pass from the speech signal to an encoded, to a latent representation of the input speech. So this is a special architecture based on a transformer. And then we use this to, together with the landmarks that represent the other input of our nectar. So you see that in this case, the input is given by the number of landmarks, 68, multiplied by 3, which is the coordinates in three-dimensional space, and the key is the number of frame in the audio sequence. And the architecture is based on a multi-layer bidirectional LSTM. And so here, probably, we can also have a quick look to the loss that we use for training. You see that there are several components: a reconstruction loss, a loss that acts just on the landmarks of the mouth, and we have also a cosine loss that tries to align the vectors of the landmarks in the ground truth and generated model, and we have also a velocity loss. So this is the representation of the cosine loss that was proposed in this work, and that resulted useful to improve the results of our representation. So basically reduce the error on the ellipse and also on the overall mesh. Here we have also some results comparing our approach with the two other works in the literature. So you see that the error in our case is quite lower than the other works in the literature. And maybe here, hopefully, if it works, because with the audio, I don't know if it can work, but...
You throw in a few options you like and see which one has the most support. It's called Pick All You Like, and you can remember P-A-Y-L, like put all the toppings you like in a pail. Put all the options you like in a pail.
But boredom is not just a problem in schools, it's a problem that tracks us beyond schools. There are several troubling addictions that are linked to boredom. When we're bored, we drink too much, we eat too much, we spend too much money, we buy things we don't need.
So this is okay, it's, again, the architecture. So I think we have some other example, okay, later. Okay, so this is again the example of the, you see the spiral convolution that we use for passing from the landmark to the mesh.
My story starts in Moscow. I was 15 years old. My best friend and I, we were part of a group of Westerners visiting the Soviet Union. This was in 1987, a few years before the fall.
Eh sì, io ho rotto gli schemi, in realtà anche tuttora, perché io anche oggi non ho neanche un tatuaggio, eppure continuo a fare questo lavoro.
Monsieur le Président de la Banque Centrale Européenne, cher Mario Draghi, Monsieur le Président de la République, cher Sergio, Madame la Chancelière.
Okay, so we have this invariance.
She had your dark suit in greasy wash water all year.
Comparison with the state-of-the-art solutions.
A crab challenged me, but a quick stab vanquished him.
And this is an example where we compare the generation with the cosine loss.
Cities across America are using the same old, tired approaches that don't actually prevent it.
Okay, so as you have seen it, with this architecture, we can generate in different languages in some way without any effort, because it's something that we inherit from the WAV2VEC encoder. Of course, this work is not, we have some limitation, because as you can see, For example, we can generate neutral phases. Of course, one possible direction, and we are working on this, is that of adding emotions to this representation. So we can generate talking heads, but with a different emotion. And in addition, you see that the movement is more or less concentrated in the mouth region of the face, but of course, for a natural appearing movement, we should have also movement of the head and something more realistic in the other part of the face. So to conclude, because I think it's quite late, probably I skip some details, but as a last example of possible application of generative model in this non-Euclidean domain, I won't just probably present just the final result of this work where we try to do the following. So suppose that you can capture 3D data, a sequence of 3D data. So this set of points represent a lot of information that probably we would like to transmit on a channel. And so probably we need, in order to reduce the data to transmit, to compress in some way the data. And there are some tools also defined by the motion picture expert group, the MPEG, which is the point cloud compression and the video point cloud compression that define how to compress. So this is standard that defines the way we can compress a stream of point cloud. But of course, compression can be with some loss, and so we can have data that we reconstruct on the user side is in some way of lower resolution, of lower accuracy. So one idea here is that of increasing the resolution of the model from the user side, and so this operation normally is called upscaling. And so in this work, we applied basically a graph convolutional network in order to perform this upscaling operation. And so the idea that we can, for example, as you can see in the figure, we can have a low resolution point cloud, so a stream of point cloud, and we can increase the resolution in a similar way to the ground truth, which is shown on the right. So probably I can skip the details and go directly to here to the results, where actually our method is not the best one in terms of chamfer distance, so of accuracy of distance between generated and the ground truth point cloud streams. But in our case, we are able to use just a few frames from the input, just 3, in order to increase the resolution. And here you can see on the right, you can see the ground truth. On the left, you can see the low resolution input, and in the middle, you see the reconstruction of the point cloud. So you can see that we are able to increase the number of points in a quite reasonable way with respect to the ground truth. Okay, so here you have several examples with different moving person. This is a particular data set that has this specific type of movement. And so this can represent another way we can use a generative model for an application that can be useful in the real world. And so let me probably conclude here. I want to thank the other friends that collaborated with me in this research. So Professor Daudi and Naima that are here from the University of Lille, and Professor Del Bimbo, Claudio Ferrari, Lorenzo Berlincioni, and Federico Nocentini at the MIC at the University of Florence. And here you can also find some references that you can use for studying more on this subject. So, thank you very much.